Hello. Having discussed already about the charges, their properties, and also the methods of charging objects, we now move over to the topic of forces between two isolated charges, and that is given by the Coulomb's law. The Coulomb's law in electrostatics states that if we have a pair of charges, namely Q1, Q2, and they are separated through a distance, let's say r, in that case we give the magnitude of the force to be proportional to the product of the two charges as well as inversely proportional to the square of the distance between them, and this is popularly also the inverse square law. And combining all of that, what we get is F is equal to some proportional constant there, and that is that results in q1 q2 over r square to be multiplied to that, and this is the expression. Now this that we have over here gives the magnitude of the force. Now if we consider the direction, we'll have to consider the application of the force. Now the application of the force is that one of the charges is going to apply the force on the other. It may be attractive, it may be repulsive. Here, since we have taken both the charges to be positive, we will be considering the repulsive force. And if Q1 is to apply the force then on Q2, then it will be applying along that line, and that will be repelling the Q2 charge along that line. So as a result of that, if I'm saying that r here is the position vector of the charge Q2 with respect to Q1, then we can have the force to be directed along that position vector, and so vectorially we can say that this will be expressed as F to be equal to that constant times of Q1 Q2 over r squared, and as far as the direction is concerned, it's along the unit vector of that position vector. Now this r hat obviously is a unit vector, and as far as this proportionality constant is concerned, it's the electrostatic proportionality constant, and that is equal to, that is expressed, that has an expression with it, that is 4 pi epsilon naught. We'll come to that epsilon naught later. We already know what 4 pi is. 4 pi is just 4 times of pi. Pi is 22 over 7 or 3.14. But this also has a value associated with it. We'll see how that value came up. So this is 9 times of 10 raised to the power 9. It's actually nearly 8.99, but still we can round it off to 9 times of 10 to the power 9. Well, what about the unit? Now the unit that we can consider in this case is that we can obtain is that because force has an SI unit as Newton, and the distance there at the bottom is meters squared taken in SI units, and this is Coulomb times of Coulomb, so Coulomb squared. So this is Newton meter squared over Coulomb squared, or Coulomb raised to the power minus 2. That is the unit of the electrostatic force constant, or probably the proportionality constant. And if we are to consider the dimension of that quantity k, then we'll have that to be equal to, well, the dimension of the force multiplied to the twice the dimension of length, and divided by twice the dimension of charge. So that gives us mlt raised to the power minus 2 for force, L square for meter squared, and charge is, as you know, at squared. So this results in ml cube t raised to the power minus 4 a raised to the power minus 2. That's the dimension of the constant term over there. And we will see, as I said, we'll see that how that value came up, but that's to be discussed later. Now this was the expression for force that Q1 applies on Q2. What about the force applied by Q2 on Q1? Because that can apply a force as well. The electrostatic force is mutual. So the force that Q2 applies on Q1 is actually equal, and it has an equal magnitude. So if I say that probably F21 is the force on the charge placed at 2, this is at 2, this is at 1, force on 2 due to 1, that is the charge at 2 due to the charge at 1, then we'll have this as F21 is equal to K Q1 Q2 over, we'll say that Q2 has a position vector, let's say R2 1 with respect to the charge at 1, and this is R21 hat. We'll describe it in a better way with another picture considering the origin and Cartesian coordinate system for better understanding. So here we consider a Cartesian coordinate system where we have the two charges Q1 and Q2, and we have this position vector of Q1 as R1 and probably the position vector of R2 as the position vector of Q2 as R2, and this gives the position vector of Q2 with respect to Q1, and this is obviously R21 that I have written over here, and in this case this is equal to R2 minus of R1. So if I substitute this value over here, so this is K Q1 Q2 over, well, this is R2 minus R1 mod squared. This is from the triangle law if you remember. Then this can be written as R21 vector over R21 mod. That's the definition of any unit vector. So this is Q1 Q2 R2 minus R1 cube, because this has got multiplied to this, and then we have R2 minus R1 at the top as well. Now this is the force applied by the force on the charge 2 due to the charge 1. So what about the force 1 2 will therefore be force on charge at 1 due to the charge at the point 2, and as a result of that what we get is we can just write this as F12 will be equal to K Q1 Q2, and this instead of the position vector will be taken the other way around, that is R12 mod squared, and this is R12 hat, or if we are to write the final expression like this, then we'll be having K Q1 Q2, you know, R12 will therefore be exactly the other way around, that is R1 minus R2 mod cube, and this is R1 minus R2 as well. Now if I were to check these two expressions, compare them, what I would see is that if I interchange these values over here, then what I get is KQ1 Q2. Now interchanging over here wouldn't really affect the value because it's in modulus, and the modulus means the magnitude, so magnitude doesn't really change even if I change the positions, the signs over there. But changing the sign over here would result in something different. This thing will become negative, and if you observe this entire expression that we have is exactly equal to this expression, and so this is the negative of F21. So F12, as we see it, is actually the negative of F21, and that is exactly the case of an action and reaction force. So if one of them is the action, the other one is the reaction force that the other charge is applying on the first one, on the former. Then also what we see is that with these position vectors uh, taken on either side, R21 if that is directed along that is directed from Q1 to Q2, R12 will be directed from Q2 to Q1. So ultimately what we are observing is that the forces are acting upon this direction towards the center of that of that of those pair of charges, and that is why these action and reaction forces that are that take place or that occur, they constitute what we call as the central force, because they are ultimately directed towards the center of mass of the arrangement of those two charges. So that is the case, the vector representation of the force between those two charges that we have just discussed, and that explains the Coulomb's law. But what we are still about to uh, what we must also consider is that epsilon naught that had come up. We'll see that how or what exactly is that particular thing. Well, epsilon is the permittivity of a given medium. It's the permittivity. As the name suggests, almost sounds like a medium is permitting something. What is it exactly permitting? It is permitting the two charges to interact between themselves. How do they interact? Well, they apply forces on one another. So permittivity of a given medium is that phenomenon or that property of the medium which through which it allows the interaction to some extent, the degree of allowance that it provides to the interaction between two charges. Now, different mediums will permit those charges, those pair of charges, those very pair of charges. If you take supposedly a proton, two protons or two electrons, or a proton and an electron, and place them supposedly at a fixed distance, you pin them in air medium, then for the same distance you take them and immerse them in liquid, let's say water, then the force will change, the force between them will change, that where it will be different from that in air than that in water. And even in some solid objects, supposedly we take them inside a glass and we pin them at the same distance of separation, we would expect that the magnitude remains the same with the definition of Coulomb's law, but the medium, with the medium changing, we'll have different values of the forces between them. So so this permittivity for air or vacuum is treated to be almost the same. We treat the air as well as the vacuum as an empty medium, and so we represent that permittivity of air or vacuum as epsilon 0 or epsilon naught, because that's there's no medium there, we consider no medium. So epsilon 0, 0 stands for the zero medium, and the value for that medium has been obtained experimentally, and that is nearly 8.85 times of 10 raised to the power minus 12. And as we have obtained the unit for K, and epsilon naught, as you know, is related to K as to be in its reciprocal, or to be in the denominator. So if K has a unit of Newton meter square per Coulomb square, then epsilon naught, with 4 pi having no unit at all, epsilon naught will be having the unit just to be exactly the opposite, that is Newton inverse meter raised to the power minus 2 Coulomb squared. There it was Coulomb to the power minus 2, here it is Coulomb squared. Now this is the permittivity for air or vacuum. Now we also have the absolute permittivity for, so there is an absolute permittivity for air or vacuum, and that is this. While the absolute permittivity considered for other mediums, because air and vacuum are frequently available, we take them as a standardized medium. So we compare the permittivity of other mediums with respect to air, just like we compare the density of any given object with respect to water, whose density is just 1 gram per cm cube. Now absolute permittivity of any other medium is simply given as epsilon, and the force in those mediums, the corresponding force in those mediums, will be given by 1 over 4 pi epsilon instead of epsilon naught, if the two charges are q1 q2 separated by a distance r squared. We're just considering the magnitude in this case. So the absolute permittivity is the one that is over there in that electrostatic force constant. And if we were to compare the permittivity of that medium with respect to the permittivity, this general standardized permittivity, that is of air or vacuum, then we relate them, and hence we call that as relative permittivity. Now the term relative permittivity is sometimes also called as the dielectric constant, usually represented with a capital K, and not to be confused with the K that I have used over here. This is in capital block letter. This we'll be using this term more frequently when we study about the capacitors, so, or probably the insulators as well. So this is just a dielectric constant, which is also equal to the relative permittivity. And the relative permittivity, as I said, is we are going to compare the permittivity of a given medium with respect to the permittivity of air or vacuum. So that's how we define the relative permittivity. Although permittivity here, the absolute permittivity of a given medium, has the same unit and the same dimension as epsilon naught. Well, if we are to consider the dimension of epsilon naught, because we know the dimension of K, it's easier to determine the dimension of epsilon naught, because it will be just the inverse of what we have obtained. So what will be the dimension of epsilon naught? You can try, I'm writing it over here. Dimension of epsilon naught will be simply equal to, because we have obtained the dimension of K, and that was m L cube t raised to the power minus 4 a raised to the power minus 2. So here it will be m raised to the power minus 1, L raised to the power minus 3, t raised to the power 4 plus 4, a raised to the power 2. That is going to be the dimension of the, you can bend your neck and see what I've written over there. Okay, now so this, but this fellow over here, this relative permittivity, because it's the ratio of permittivities, it does not have any unit or dimension associated with it. This is just a number, an index of a given medium. So when we know the index of that medium, we also have the information about the permittivity, absolute permittivity of the medium, because we know the absolute permittivity of air or vacuum, which is epsilon naught. Also from this definition, what we can say is that the relative permittivity is also, it can be defined as the force between two given charges in air divided by the force between them in that given medium, so that for the same distance of separation between the charges, of course, we maintain the distance of separation, and in air we have 1 over 4 pi epsilon naught q1 q2 over r squared, and then in the medium we have 1 over 4 pi epsilon instead of epsilon naught, and q1 q2 divided by r square, maintaining the distance between them. And so we have the relative permittivity as well, these two terms, they cancel out completely, 4 pi's cancel out completely, we simply have epsilon over epsilon naught is the same thing. Now from this, what we also get to know is that having the knowledge about the relative permittivity, allows us to not only obtain the value of the absolute permittivity of the medium given by this relation, which is obviously obtained from this, but also what we obtain from this relation is that the force in air is equal to epsilon r times the force in the given medium. Or conversely, we can also write that force in a given medium for the same distance of separation between the two charges will be equal to the force in air. Instead of air, I can write F naught as well, divided by the relative permittivity of the medium. So these are very useful equations in order to solve a few numerical cases that usually are associated with these kind of questions. So in case, so let's try a few numerical ones, since we have learned so many formulas associated with the topic. So now if I were to determine the force between two electrons placed in air separated by, let's say, 2 centimeters, what will be the force if the distance of separation is halved? I'm calling that out, so don't go by my handwriting. I know it doesn't look good there, but it's okay. I'm calling that out. So what will be the force now if the distance of separation is halved? And then I'll also add to that what must be the relative permittivity of a medium such that the new force, means the second one when the distance was halved, new force with, let me write that down, with the distance halved will be equal to the previous value, which when the distance was not halved, the original distance, previous value when placed in that medium. Well, all the ingredients of what we have studied so far, we'll see what we can do. So as far as the solution is concerned, let's try. So if we have two electrons having a charge 1.6 times of 10 raised to the power minus 19, as you know it. And so from the Coulomb's law, we have the force that is in air, let me write that as F naught, is 9 times of 10 raised to the power 9 Ka. Q1, Q2 is that of the two electrons, which is 1.6 times of 10 raised to the power minus 19. It will be multiplied to itself, so I can square it out. And then we have the distance of separation between them to be 2 centimeters, which is 2 times of 10 raised to the power minus 2 in meters, of course, squared. So this is the value of the force. We haven't obtained the value yet, but this is going to be the value of the force in Newton. We are concerned about the magnitude of force. Now this when you multiply that, what you will get is there's a 16 over there, and there will be a 4. I can take it as 16 times of 10 raised to the power minus 20 to simplify, just to simplify, and 16 times of 16 divided by a 4 in the denominator. So I have 9 over here, 16, and one of the 16s will get cancelled with the 4 in the denominator to give 4. I'm cancelling them directly. You can calculate 10 to the power 9, and 10 to the power minus 20 squared is 10 to the power minus 40, and 10 to the power minus 4 in the denominator when taken up is 10 to the power plus 4. This is what we end up with. So 9 times of 4, 36, 36 times of 16. Well, 36 times of 6 is 216 if I'm not wrong. 216, no, not 216, I guess, yeah, it's 216, it has to be. So 36 times of 6 is 216, 216 and 360 is 576, I guess. Yeah, I may be wrong, you can check for yourself. 576 times of 10 raised to the power minus 27, and that can be written as 5.76 times of 10 raised to the power minus 25, 25 there. So that is in Newton. But what was our concern is that if the distance is halved, that means 2 becomes 1. So there won't be any cancellation of this 16 that would have come up over here. So 2 becomes 1, square of 1 is 1. So only 10 raised to the power minus 2 in that would have been squared, and that is already taken over here. So now let me take that as F prime. F prime is the new force, which is now equal to, because 4 isn't divided, so 4 is multiplied to this factor. So I will just multiply a 4 to this, because distance, it is inversely proportional to the square of the distance. If the distance is halved, so the previous force distance is halved, then it's going to be 4 times of F naught. So that means this factor that was there, this 576 times of 4, now 2000 for 500, but what about 76? Well, 280 plus 24 is 504, right? Yes, 504, sorry, 304, not 504, 304 and 2000 over there, so 2304. When you multiply 9 and 1.6 squared, it's actually 23.04. So this number, you will come across this number quite a lot. So this is 10 to the power minus 7 if I take the power terms over there to the left side. So this is 2.304 times of 10 raised to the power minus 24 Newton. So the force has increased, isn't it? Now to bring that back, we need to divide it by 4 again. So in order that this new force will come back to this value, we need a medium which needs to have relative permittivity such that when that is divided to this new value, this is new value F naught, F prime, suppose, that will give F naught. So F naught will be back when we have F prime to be divided with epsilon r, and in that case I'm writing it once again, F prime divided by epsilon r, and in that case, because we already know that F prime is 1/4 of F naught, so F prime is actually not 1/4, sorry, F prime is 4 times of F naught, so this is 4 times of F naught over epsilon r. So F naught cancels out, there's 1 over here, so epsilon r cross multiplies to that 1, and that has to be equal to 4. So the relative permittivity of the new medium in which it will be placed with the new distance, that is the halved distance, with that halved distance, if it is placed in a medium having the relative permittivity to be equal to 4, then it will regain its original value of the force, that was 1/4 of that. So this is just an example that I tried. There will be many more questions related to it. We'll try many more numericals. We'll be doing that in another video. Till then, thank you for watching.